time for this one. Okay, we've got a roller coaster doing a loop-de-loop. I want to know which one shows the forces on the car at the top of the loop. So at the top of the loop, we've got mg down. We've also got our normal force from like the seat pushing on our butt. So that's the normal force. So the right answer is E. And you might think that's a crazy gross drawing. I don't like that. We're not in balance. We're not at equilibrium. That's wrong. We're not at equilibrium. We're accelerating. Okay? So not equilibrium. And it's not supposed to be. We are accelerating. Alright, which means our arrows won't balance. And that's okay. Okay, so these add up to our centripetal acceleration that are going down here. So the sum of the forces equals ma. And the sum of the forces in the direction, in the same direction, add up to that acceleration in that direction. So the sum of the forces, we're going to have mg plus the normal equals mac. mg plus the normal equals m v squared over r. And then they'll give you some of these letters and you'll calculate to find the other. But that's how you get started on those. Rolling friction can be neglected. Good. I neglected that. Okay, a coin. So I thought I would need to show my face to like show circle things, but maybe next video I don't have my face. A coin sits on a turntable. As the table steadily rotates, what forces are going on? So if we're rotating like this, and the coin stays put, that means we have some sort of center-seeking force keeping us on here. Alright, and that center-seeking force has got to be friction. Okay, so that's going to be friction pointing in. We're not going to also have centripetal force pushing in, because the friction is the centripetal force, okay? That's where it comes from. So the static friction, it's not moving. Yes, it's just static friction. So this is the correct answer. It's just static friction pushing us in. Centripetal force is not its own new force. It's just a label that gives the direction of a force that we've already talked about. Okay? There are forces, otherwise we wouldn't be accelerating, and none of the rest of these make sense. Some of them make a little bit of sense. But A is the correct answer. Okay. So we've got a car on a banked road, probably on planet Earth. So I'm thinking we gotta have mg going down. So that eliminates a couple. I'm thinking we got a normal force at an angle, which eliminates none. You're expected to know that. If we are not sliding, then we got friction. You know what? The normal force is holding us up. So I think friction is going down the road. It's keeping us from sliding out this way, right? If this was a really slippery, icy road, we would swoop. We would lose our footing and go that way. But because we have friction, we don't. So our friction is going this way. When I think about what direction is friction going, I just imagine if the world was frictionless, which way would this thing slip? So friction goes the other way. Alright, so friction's got to be going down like this. Okay, so the friction and our normal force are always going to be at a right angle to each other. So that's another way to help tell that it's not A and it's not B. Because friction and normal, they got to be at right angles. Okay, so I really hope it's E. Okay, good, it's E. Good. Yeah, so the net force is center-seeking, but there's no individual force that's center-seeking on this one. It's part of the normal force and part of the friction force. This would be a really difficult math problem. Okay, so we have a car on the top of the hill traveling with the velocity. So at the top of the hill, we've got our weight going down. The weight never changes, but we are going to have less normal than normal. Okay, so we've got mg down and slightly less normal than normal. Okay, so we're going to be a little bit weightless. Remember, weightlessness is just normal forcelessness. Okay, so we're going to have a little bit less heaviness. Alright, so So that's how you do that. That's a terrible explanation. I'm so sorry. Where are we with time? We're good. Okay. Oh, this problem. This one's fun. Okay, so this lady, she's got, she's not sliding up or down. So we know up and down have to balance. So it's not that one, not that one, not that one. Otherwise, she would be actively accelerating up or down, and she's not. And then we have to see, is she being pressed into the wall or out of the wall? Ooh, I was gonna pick A. E's really tempting because I've ridden one of these and it does feel like you're like trapped against the wall. I think it's A though. I think it's the normal force of the wall pushing her in. That is a center-seeking force, and the center is that away. Ooh, why isn't it E, though? Sure feels like E when you're on the ride. It's A. Yeah, it's A because physics reasons. But why? I don't know. If you put E, I get it. I get why that's tempting. So we've got mg down, normal up. No. Friction up. Okay, because if this was like made of ice and really slidey, if you were wearing like, I don't know, like a rain jacket that was all slippy slidey, you'd be maybe sliding down, and you wouldn't want that. You want like a jacket made of sandpaper that's gonna like really grip, right? So you want lots of friction so you don't slide. Okay, and it's the normal force from the surface. That's what's keeping us there. If there was no surface, the whole thing wouldn't work. Okay. So, oh, y'all can tell I practiced. How embarrassing. Okay, so on this barrel of fun, we've got, how does the normal force change if the speed changes? All right, so we are going around even faster, okay? So the normal force, so the sum of the forces in the same direction, there we go, F equals ma. So this net force in the direction of this centripetal acceleration is just normal. Her mass is m, and the centripetal acceleration is v squared over r. I'm wondering what happens if the angular speed doubles. Okay, I know this v is an angular speed, but they are proportional, so it doesn't really matter. So if we double that, note that this is squared. So if we increase what's proportional to v squared. So if we increase v by a factor of 2, so if we do 2v squared, that ends up being 4v squared. So we end up increasing the right side of the equation by 4, which means we have to increase the left side by 4. So we quadruple, okay, just by doubling the speed. Okay. Just gotta be careful if you're operating roller coasters. If you double the speed, you're 4 times in the force. Could be dangerous. Okay. Ooh, planets. No, we got time. Okay, so if we've got, let me scoot my face out of the way. Oh, the force of x on y is F. What's the force of y on x? Also F. Okay. Newton's third law. Equal and opposite. It feels weird, but the force that planet Earth pulls on me is a huge deal to me. It affects most of my life. All right, it's pulling me down constantly. However, I am also pulling up on the Earth an equal amount. We affect each other the exact same. Earth doesn't care as much because it's got a lot of other things going on. But the pull that the Earth has on me is the same as the pull that I have on the Earth. Okay, notice in this formula we have big F equals big G, m1, m2 over distance squared. There's not a direction here. It's not like, oh, this mass is the one, and this mass does the other thing, and it's a totally different formula. Like the force of 1 on 2 is the same as the force of 2 on 1. Like it's the same. Because they pull the same. There's no direction or anything implied with this force. They're both pulling, and they both pull the same. Okay, even if different masses, doesn't matter. It's the same.